In this video, I'll introduce certain boost derived converters. These converters will be helpful to you for carrying out your project or for understanding the synthesis of high gain DC to DC converters. In due course of this video, I will be letting you know certain high gain structures, diode capacitors, coupled inductors, and the way we connect two boost converters. That is called as an interleaved configuration. So these 3 or 4 details, for circuit details, for structures, I will be introducing them to you. Let's start with the circuit diagram of a classical boost converter, and then I will tell you how the subtle modifications are done so that we end up with enhancing the voltage gain of a classical boost converter. Now, in a boost converter, we will have the classical input DC source followed by the energy storage inductor, which I indicate as L, and the switch, which is denoted as S. There will be the diode D followed by the capacitor, which is used to filter the output voltage. This is the structure of a classical boost converter. Of course, I indicate the load by a resistor R, and we will be obtaining the output voltage across the load terminals, that is indicated as V0. We can enhance the voltage gain of this boost converter by using a structure which is called as voltage multiplier cell, abbreviated as VMC. This will be the first structure that I will be introducing to you, VMC. There is a base paper for this which appeared in an IEEE transaction, first in a conference and then in an IEEE transaction in the year 2008. It was by group of authors. The first author happens to be Prudente. So if you want more information, you can refer to this paper. The structure of the voltage multiplier cell is going to consist of 2 diodes and 2 capacitors. The arrangement will be like this: diode, capacitor, followed by another diode, and there will be a capacitor which interconnects the 2 diodes or 2 ends, 2 ports as well. Now the convention is to name them as multiplier diode 1, multiplier capacitor 1, multiplier diode 2, so on and so forth, multiplier capacitor 2. Now the ports that are available to the user, they are going to be interconnected between the output of the boost converter just before the load terminals. That is, they will be connected here. I will highlight this. This will be the point where the multiplier cell is going to be fixed, introduced. One can have n number of such cells. I will show you a structure where 2 cells are placed, and I will give the voltage expression for that. You can refer to the paper, as I had mentioned earlier. You can refer to the paper for detailed derivation, detailed operating principle, and other information. Now, very quickly, the structure is going to look like this. There will be the boost converter. Now we are looking at boost converter with 2 VMCs. So it starts with an input which is Vn, then there is the energy storage inductor L, then the switch S. Now the cell is introduced. I will introduce the first cell here. This is the first VMC. Then I'll introduce one more such cell. I will just put a dot so that would mean you can have n number of such cells. I'll just introduce one more cell for additional clarity. then the classical boost rectifier diode, and the filter capacitor or the output capacitor, followed by the load arrangement. Now the cell is, there are actually two cells. I will name the components and then I will indicate the cells as well. DM1, CM1, TM2, CM2. This is one cell, cell 1. VMC1, and there will be another cell. There is another cell which is this one. This is the classical boost rectifier diode D0, and this is C0. D0 and C0, they don't change, they will be there. So this is VMC2. Now the overall voltage gain of this circuit, which is shown over here, is given by, of course, this is the boost converter with two VMCs. Boost converter with two voltage multiplier cells. V0 by Vn, which is the output voltage obtained across the load terminal. Now, voltage gain V0 by Vn is given by 1 by 1 minus D will be for the conventional boost converter. D is the duty ratio, and each VMC cell sees a voltage, input voltage of 1 by 1 minus D. So if you are using two VMCs, it will be 2 by 1 minus D. So totally it will be 3 by 1 minus D. For a boost converter with two VMCs, the overall voltage gain will be 3 by 1 minus D. Generically, for n VMCs, if one keeps on adding many such voltage multiplier cells, the network will keep on providing more voltage gain, or that is the understanding, but actually it doesn't happen that way. I'll write the voltage gain expression and then I'll tell a little bit detail what happens when we keep on adding more number of diodes and capacitors. For n VMCs, the generalized voltage gain expression V0 by Vn is given by 1 by 1 minus D will be for the boost converter, because there are n VMCs, each VMC cell will provide a voltage gain of 1. So totally it will be 1 plus n by 1 minus D. This will be the expression for voltage gain in case there are n VMC cells. But practically, the number of VMCs that we add to the boost converter, we just cannot add more than 5, 6, 7, etc. because each cell, there are 4 components that are added. So practically that the diode will have a voltage drop across it. As a result, the next stage, subsequent stage input is going to be reduced. Theoretically, yes, we won't have any voltage drop across the device. However, practically there is a voltage drop. Resultantly, if we keep on adding more number of cells, we won't get 1 plus n. It will be reduced. Not only that, because there are more components, the power loss will also be more. So the efficiency of the system, of the circuit, that is going to be drastically reduced. Nevertheless, compared to a classical boost converter, if one chooses two VMCs, let's say this circuit, then comfortably one can obtain a voltage gain of around 4 to 5 times. 4 to 5 times, that's easily possible. 4 to 5 times the voltage input, or voltage gain, which is 5 times the input voltage. This is quite comfortable. For instance, when one operates at a safe duty ratio of D equal to 0.5, 6 times gain can easily be achieved. 3 by 0.5, that will be 6 times. So that can easily be exceeded. Whereas in a classical boost converter, you should have seen in my earlier video, when the duty ratio is increased beyond 0.8, there was severe voltage drop across the device, there was a severe reduction in the output voltage. So classical boost converter is fine till the voltage gain is 4. Beyond voltage gain of 4, some techniques have to be thought about. Using voltage multiplier cell is one such technique, where voltage gain more than 4 to 5 times. Probably I'll write more than 4 so that you will find it easier to understand. More than 4 to 5 times this is possible. Six times, as I was mentioning, at D equal to 0.5 is quite easy. This is first technique. The second technique would be, instead of having one boost converter alone, if we need a higher power level, we can actually interleave the boost converter. And interleaving would mean that one brick or one boost converter is connected in parallel with the other boost converter, but actually the gain of a interleaved boost converter will not be increased. So the way we connect the second stage, that can be slightly modified. That is called as voltage lift technique. Voltage lift technique. This is the second technique. Sorry, TECHNIQUE. Now in voltage lift technique, quite obviously there will be an interleaved stage. So interleaved concept is also required. Interleaved, as I was mentioning, means two converters are in parallel. So which is interleaved boost converters. More than one. When we use a two-phase interleaved boost converter, then the two stages, two-phase IBC, it would mean there are two boost converters in parallel. Let us see the structure in detail. I will name this as L1 because there are going to be two boost converters. To distinguish one from the other, I will name them as L1, S1. This forms the first stage. Quite obviously, the boost converter will be grounded or connected to negative. That is going to be connected in parallel. So the second stage, I will name the components as L2 and S2. The supply is going to be common for both the boost converters. So it is going to be like this: plus minus supply, which is Vn. This is also grounded. I hope you can understand, because you need two bricks which are going to be arranged in parallel with one another. One brick followed by the other in parallel. They will be in parallel so that the connections can now be comprehended. Understand that they are in parallel. Now the remaining elements. There has to be an output capacitor and the boost rectifier diode. That stage will always be there. That I will draw at last. Now actually the boost converter 1 or stage 1 will have an output diode. I will name this diode as D1. Boost converter 2 will also have another boost rectifier diode, which I draw and name this as D2. Now the classical way would be to connect the output obtained from, let's say, boost converter 2 to a capacitor, and then that will be grounded. Similarly, we connect a capacitor and then we ground. That would mean two boost converters are in parallel. Instead of doing that, we lift the voltage by introducing a lift capacitor which is connected like this. This capacitor is called as lift capacitor. I will name it as C lift. Now effectively, instead of grounding this voltage obtained from stage 2, I am lifting and making it get stored across C lift. So this is called as voltage lift concept. When converter 1 operates, again the energy stored in the inductor will be transferred to C lift when the switch S1 is off. Now when you try to understand the operation in detail just a bit, let's say when the way the interleaved stage operates or interleaved boost converter operates is, the switches, they are going to be complementary with one another. I will indicate that as well. S1 and S2 complementary, meaning 180 degree out of phase. That's all. 180 degree phase shift. That would mean only one switch is going to be on at a time, the other switch will be off. One point. Another point is, because S1 and S2 are going to be complementary, the current that flows through the boost converter, input current, is going to be shared. Those are features of interleaved stage that you can understand by referring to various papers. But now the circuit, there has to be a slight modification. That's why I took up this. Let's understand what happens when S2 is on and S1 is off. The stored energy in the inductor should be transferred to capacitor, but there is no path for this because this diode D2 will be blocking. When S2 is on, L1 should transfer its stored energy to C lift. That doesn't happen. Therefore, you can reduce this D2, or rather you can disconnect this D2 and keep it elsewhere instead of D0. Definitely there has to be a D0 and C0 stage. So what you can do is slight circuit modification. I will strike off D2 and then I will arrange so that you understand the circuit without D2. This D2 will not be there. Instead, we will save one component, one element, by having the classical D0, classical boost rectifier diode, and there has to be a classical output capacitor. Then we have the load arrangement. That's all. This is the actual circuit. Or we tap the voltage across the stage V0. So you won't have this diode. That will help actually in making C lift or storing energy across C lift. This is how the two-phase interleaved boost converter with a voltage lift capacitor works. I will write the circuit arrangement, name of the circuit arrangement. This is two-phase interleaved boost converter. I will abbreviate and write it as two-phase IBC with voltage lift technique. The voltage gain expression for this circuit is given by V0 by V in will be 2 by 1 minus D instead of 1 by 1 minus D. Because we have lifted the voltage across the first stage, it's quite simple to understand. If you are familiar with the classical boost converter, it's quite simple. I'll try to elaborate that as well. See, across this point and ground, the voltage gain will be 1 by 1 minus D. Again, between this diode and ground, the voltage will be 1 by 1 minus D. Because the capacitor C lift is connected in such a way that the voltage levels get added up, the net voltage available across D0 and ground will be 1 by 1 minus D plus 1 by 1 minus D. That is going to be 2 by 1 minus D. This is how the two-phase IBC with a voltage lift capacitor works. Again, compared to a classical boost converter, the voltage gain of a two-phase IBC with voltage lift is two types, it's actually doubled. So this also provides a voltage gain which is higher than the CBC. This is the second method which is used to enhance the voltage gain. Third method would be, we have used only simple inductors, L1 and L2, they are actually simple inductors. Instead of using simple inductors, we can actually use a coupled inductor, where primary is used for the main energy storage element. At the secondary side, we can connect gain extension cells as well. So that circuit I will draw. That is another variation. That is a third variation that can be thought about. Third variation is using coupled inductors. Third method of enhancing the voltage gain of a classical boost converter, using coupled inductors. I will just draw a simple boost converter with a primary winding which is used as the energy storage inductor. At the secondary side, I will connect diode capacitor multiplier cells, and then I will tell you how to couple the outputs using coupled inductors, which I abbreviate as CI. In all the networks that we have come across so far, the first stage will be a classical boost converter stage. No change in that. So we'll just have the classical boost inductor. Switch S1. Now remember, the inductor L1 is going to be replaced by a coupled inductor. So at the secondary side, there can be some variations. This is the boost converter part. D. For the time being, I will just name this as C alone. Depending on the network arrangement, I will rename it. As I said, secondary side, there will be another voltage gain that is going to be possible. So that is what I am drawing now. For clarity, I will change the color. Now this is the secondary inductor, which I name as L2. Remember, they are coupled. So that coupling is indicated by this core. Again, for additional clarity, I will join this, though it is not required. Just put a core and indicate that is sufficient. But if you are encountering this for the first time, this may be useful to you. It means that both the windings L1 and L2 are placed in the same magnetic structure. There will be a E-type core, or there will be some other type of core. It could be a toroidal core as well. Same magnetic structure, we place both the windings L1 and L2. That is called as a coupled inductor. Now we have other arrangements which include a capacitor, a diode. Now these two elements help in transferring the energy stored in L2 to, I will name this capacitor as C2 now, and this diode as D2 now, which would mean the earlier element was D1, should have been D1, this is C1. Now the outputs have to be coupled, or they have to be tied with one another. So that tying arrangement is through this. This is D0. Now there will be another capacitor which is C2. If you observe carefully, output from the classical boost converter stage which is obtained across C1 and the output from the secondary side which is obtained across C2, they are not tied with one another. So the tying arrangement will be the final thing. The tying arrangement or connection is obtained like this. And finally, we will be obtaining the load voltage across the entire structure that involves the boost converter and the secondary side. This is the load resistance. I will indicate it as R load. The output voltage is obtained across this V0. Fine. Now very simple observation and intuition would tell us that the voltage gain of the network that is shown over here is given by V0 by V in will be 1 by 1 minus D will be across C1 for the boost converter stage where the primary inductance is used, and the secondary side there is another inductance L2, and then there are other cells C2, D2 that forms the diode multiplier cell which I was suggesting earlier. The turns ratio between L1 and L2 can be adjusted. That is the beauty of the coupled inductor. I will write this as 1:n, which means by having many turns across the secondary compared to the primary, multiple number of turns, the output obtained across L2 can be enhanced multiple times, many times. Therefore, by simply having a structural arrangement which is shown over here, the voltage gain can be enhanced. In that sense, if we want to quantify, the output obtained from the secondary side will be given by n by 1 minus d. Remember, in this case, n is the turns ratio. Earlier we had come across voltage multiplier cells where capital N was the number of voltage multiplier cells, number of VMCs, whereas in this network, n represents the turns ratio. Exactly similar to what we would come across in a transformer, 1:n, where n remains the turns ratio. This is how we enhance the voltage gain of a classical boost converter using coupled inductor. Fine. Now, these are three techniques which I have introduced. One can actually have combination of all these three things. In fact, you can have a two-phase interleaved boost converter with a VMC with n number of VMCs. That is possible. In that case, the voltage gain would be 2 by 1 minus d for the classical two-phase IBC with voltage lift, plus let's say if you connect two VMCs, that would be another 2. So you will have 4 by 1 minus d for a two-phase IBC with two VMCs. One variation. Another variation could be in a two-phase VMC, rather two-phase IBC with voltage lift, you can have coupled inductors and then you can have two secondaries. So that would further enhance the voltage gain. That is also possible. So those are possible variations which one can think about. This is how high gain boost converters are actually synthesized. I am sure this would be useful to you. You can actually work on various techniques, various voltage gain enhancing techniques. In case you have any clarifications, any doubts, feel free to mail me. I'll be glad to clarify your doubts. Thank you.